So, welcome back to the Libra online seminar. Now it's time for our third speaker of today to give his presentation. Michael Röckner from TU Berlin, welcome. And he's going to speak about the p-Laplace operator and the p-Brownian motion. Please, the stage is yours.
Yeah, thank you, Jonas. So first of all, I want to say thank you very much for the kind invitation. I think it's really a great idea to have such online seminars. So thanks a lot. I'm very happy to be here. Second point is I want to apologize for not being here earlier. So I presume there have been 2 talks already. Thirdly, I want to apologize for having to leave immediately after my talk. So I can also not stay for the last talk because I have to catch a train. But anyway, so I'm very happy for you to be here and for having me. Right. So this is a relatively recent project I've been working on with Michael Röckner from Bielefeld and Viorel Barbu. And okay, so if you want to know more details, this is available on arXiv. It's to appear in AOP, but to be honest, I'm not sure whether it has appeared already, but you can essentially find the latest version more or less here. So this is about the p-Laplace operator, and the essence in one sentence or in one line that we did in this paper is, as you all know, this I will recall in the next couple of pages briefly, there is a very prominent and deep relation between the heat equation and Brownian motion, right? And our basic but non-trivial question was, if you replace the heat equation by the p-Laplace equation, is there a similar natural probabilistic counterpart? Okay, so this was basically the underlying question. So let's get going. So this is the outline, but I think it's not necessary to walk you through the table of contents. We'll just proceed as we go. So as I promised, this is a brief repetition. To be honest, I was not exactly sure about the audience here, but certainly what I tell you on the first 1 or 2 slides here is not a surprise to anybody, but still is important to recall because this makes it much easier for you later on to compare to our new result. So as I said already, I mean, this is one of the cornerstones, if you like, of PDE theory, linear PDE theory and stochastic analysis, right? So you have this very nice, beautiful basic relation between the heat equation and Brownian motion, more precisely in the following sense. So you have the heat equation, the factor 1/2 is just for, technical convenience. You can also trade this away to have a factor in front of the Brownian motion. Anyway, so you have a Brownian motion, then of course you know that if you look at its one-dimensional time marginals, so you look at the distribution of the Brownian motion at time t. For a moment, let me denote this by mu t0. The 0 will make sense in just a second. Then you know that this is given by the fundamental solution to the heat equation, more precisely in the following sense. If you look at the classical heat kernel, centered at 0, right? So later on, this will in a sense denote our initial condition, if you like, and y is the space variable. Then, of course, the distribution of Brownian motion is just given by the density, right? So density of Brownian motion at time t is just the heat kernel at time t. Maybe just a word on notation. So this curly L of a random variable I use for the distribution of this random variable. And more importantly, this will also appear when here we do not have a real or RD valued random variable, but the whole process. Okay, so when I write this and there is no subindex t, then this means the path law of Brownian motion, for instance, or the path law of any other stochastic process. And whenever I put the t, then this is really a real or RD valued random variable, and I mean the distribution on RD. Okay, so this is standard, right? And of course you can play this game a tiny bit more generally. Of course, nobody can stop you from considering x not being 0, but arbitrary x as your initial condition of your Brownian motion. In other words, you just shift your Brownian motion by x and you look at the corresponding curve of one-dimensional time marginals. And what you will find, of course, is that this is just given by a density being the heat kernel centered at x. So again, x is the center of mass, or if you like, the initial condition, and y is the free space variable. Okay, and just to go on with a couple of obvious remarks. Of course, this Bx, this shifted Brownian motion, is obviously the unique, if you like, even strong solution to this trivial SDE. I'm only telling you this so later on we can compare to the stochastic equation that we derived, but of course here is completely clear. And finally, the third object I want to introduce, because there is also a natural connection later, or a parallel development later for our p-Laplace case, is that if you look at this family of path laws, okay, so here appears the notation I mentioned before. So you look at this family of path laws, so in a sense the shifted Wiener measures, if you like, they form a Markov process, okay? And Markov process for us always means a family of path laws, so it's not a single stochastic process, but it's a family of path laws indexed in X, and they satisfy this Markov property, okay? It's just the usual thing, so we do everything on the canonical space of continuous functions, and you have the usual projections at fixed time t of a path. And you see it's really necessary in order to formulate this Markov property to have this family of path laws, because when you let your omega run here, you can, you will produce basically every space value, say y here, so you really need each path law omega y, okay? So a single omega x is not sufficient to formulate this. Okay, so this forms a Markov process, and of course its transition kernel is just given by the aforementioned measures with density given by the heat kernel. So just to wrap this, in a sense, trivial or well-known repetition up, so what is the conclusion? You start from a PDE, the heat equation, okay? You look at its fundamental solutions, and you find that you can have a probabilistic understanding of these fundamental solutions, namely as the family of one-dimensional time marginals of a uniquely determined Markov process. And this Markov process consists of solution path laws to a certain associated SDE. Okay? So you have, if you like to have in your head kind of a diagram, you have three objects. You have the PDE with its fundamental solutions. You would like to associate a stochastic differential equation to it, such that you can solve this SDE. The solutions of this SDE, in the best case, which is of course the case here, they will be unique, okay? And their one-dimensional time marginals give you back the fundamental PDE solutions, and these solutions of your SDE form a Markov process.
Excuse me?
Sure.
So what does this notation with the conditional on the filtration mean? So is it a conditional expectation or?
Ah, sorry, you mean this left-hand side here?
Yeah, yes.
Yeah, sorry, I didn't mention this. So this is the usual filtration on the canonical path space. So Fs is the sigma algebra generated by all time projections for times t between 0 and s. Sorry, I should have said that. And yes, then this is just usual conditional expectation.
Okay. So it's conditional expectation with respect to Wx. So
yes, exactly. Yes, right. So
okay, this was
right. Yeah. Right. So this is a probability measure on this set. You have a filtration on this set. A is a Borel set from RD. So this is an event in this basic space here. You have your filtration, and you consider conditional expectation with respect to your probability measure Wx, which is the path law of the shifted Brownian motion. That's fine.
Yeah, sure, it's okay. It's just
okay, great. Okay, so if you try to keep this conclusion in mind, then what we turn to next will appear a natural question to you. So now forget about the heat equation. Let's consider the p-Laplace equation, the parabolic p-Laplace equation. Okay, so you have your p-Laplace operator here. We stay in the regime p strictly greater than 2. Okay, so if you like, we don't go to the, let's say, fast diffusion case in a certain sense. And of course, for p equal to 2, this just gives you back heat equation. Okay. And well, then first of all, you can ask, okay, what is the analog of the heat kernel? Well, strictly speaking, there is no analog in the sense that you cannot expect to have fundamental solutions in the strict meaning, where for me, fundamental solution means you can produce solutions for arbitrary initial data by taking convex combination of these fundamental solutions, which of course doesn't work in general if you have a nonlinear equation. But nevertheless, what does exist are explicitly given solutions, and these are called the Barbu solutions. Okay, so they have a point source initial datum, so center of mass is a point x. So again, x denotes the initial condition and y denotes the space variable, and these are explicitly given. And I don't want to talk too much about these explicitly given solutions. I mean, just right away you can see, for instance, they are compactly supported because you have the positive part of a certain function here. So they have compact support, and the support spreads out in space. In time, right? So if you let time go to 0, then this collapses to a Dirac measure. And if time goes on, this flattens out and the support grows. It's, of course, I mean, obviously it's a non-negative solution. I don't want to talk too much about the Q and the K here. I mean, these are just constants which are uniquely determined in the sense that the equation is actually solved. And the C1, you can basically choose anything, but for us, we choose C1 specifically such that for every fixed t and x as a function in y, this is a probability density. And this is a straightforward calculation that such C1 exists. So you should think of these, for each fixed x, you should think of this, if you like, as a family of probability densities indexed in t. And of course, I mean, as you can guess, you have certain nice regularity aspects of this guy in t and y, and this is a solution to the p-Laplace equation, okay? And these are called the Barbu solutions. Okay, and now the natural question, at least natural compared to the previous slide, is the following. So is there an analog connection to stochastic analysis to probabilistic counterparts as for the heat equation and Brownian motion? So a bit more precisely, we have the PDE, right? We have the solutions we are interested in. For every x, we have a solution with initial datum x, and these are probability solutions. So can we find an associated stochastic differential equation that we can solve, possibly or hopefully even by unique solutions, in such a way that the one-dimensional time marginals of these solutions have densities which are exactly these Barbu solutions? And can we do this in such a sense that these unique SDE solutions, or more precisely their path laws, form a Markov process? And if so, then maybe this appearing Markov process or these appearing unique SDE solutions could be deserved to be called p-Brownian motion. Because then really, if you go back to p equal 2, you recover exactly the usual Brownian motion via this ansatz. Okay, and our answer is yes, you can do this. And we did this in the paper. And this is obviously the main result I want to present. I will present this result by doing quite a bit of a detour. So I hope this is not, let's say, too demotivating. But if you look to the table of contents here, the main result is really the end in a sense. Okay, so okay, because the way we achieve this result is we apply and at the same time significantly extend a certain general approach which allows you to connect certain classes of nonlinear PDEs to their natural probabilistic counterparts, which are in this case solutions to certain McKean-Vlasov, or if you like better, distribution-dependent SDEs, and also to certain so-called nonlinear Markov processes. And I would rather briefly walk you through this general approach, and then I tell you how we apply this precisely to the p-Laplace equation. And these are all rather recent developments. So let's say very roughly, probably, I mean, this specific field was probably initiated or became prominent maybe about 10 years ago, let's say. Okay, and it all starts with so-called nonlinear Fokker-Planck equations. So these are second-order parabolic PDEs for measures, okay? So of course, we'll come back to proper PDEs, I mean function-valued PDEs in just a minute, but for now, let's stick to these measure-valued PDEs. So solutions are curves of probability measures, mu t, okay? And I'm not going into detail here about the notion of solution, but it's distributional. So this means you put all derivatives on the test functions against which you integrate. So in particular, we do not assume or expect here any regularity of the coefficients a, b. Sorry, this is a typo. This should be aij. So this is a matrix. So you do not expect any regularity of a, b, and of course, in particular, not on the measures. So we are not assuming that you can differentiate a measure here in a weird sense. Okay, and then once you have such a nonlinear Fokker-Planck equation, there is always an associated SDE, which in this case is the Vlasov equation. And I will tell you exactly what associated means. So on the formal level, you can just read the association of, because you take the same drift, right? And you take essentially the square root of the diffusion. But this is only formal, I mean, in terms of symbols. So what is really the mathematical relation? And this goes both ways. So if you have a weak solution to the Vlasov equation in the usual sense, basically just by applying Ito's formula, when you consider the curve of its one-dimensional time marginals, this gives you a solution to the nonlinear Fokker-Planck. So if you have a process solving this equation, by looking at its one-dimensional time marginals, you always get for free a solution to this equation. Okay, so this is the easy direction, which is a two-line proof. The converse direction, as you can imagine, is much harder, because here you start only, so assume you have a solution to this equation, okay? So you have a curve of probability measures on RD. You want to construct from this a stochastic process, or in measure language, a path law, so a much richer object, which solves this equation. So you can imagine this is much less of a trivial thing than going in this direction. But indeed, this is also possible. This is the so-called celebrated superposition principle. So this started with Ambrosio and Figalli about, say, 20 years ago. And then the main contribution was here due to Dario Trevisan about 10 years ago or 12 years ago, I think, in his PhD thesis. And this tells you the following. So if you have a solution to this equation, in a certain sense, so you have certain, let's say, integrability of the solution against the coefficients, but this is quite mild, so I'm not going into detail here. Then you can always construct, and I'm really saying construct and not find, but construct a solution to the Vlasov equation X, which has the prescribed one-dimensional time marginals. And this works without a priori knowing whether you have solutions here. So if you give me a Vlasov equation, which is pretty bad, yeah, so you do not have good regularity, you don't have a well-Posner theory. If you are lucky and someone from, outer space tells you that there is a solution to the corresponding Fokker-Planck equation, then you can always solve this equation. And you can even prescribe the one-dimensional time marginals. Okay, so this is, as I said, relatively new stuff, say about or less than 10 years, but it's known. So this is not our contribution. So this relates in a nonlinear setting very nicely PDEs, or let's say Fokker-Planck equations, and SDEs, Vlasov equations. And so how about the third object that we had in the classical heat equation case? We had Markov processes. So natural question is, if you have a very nice Vlasov stochastic differential equation, yeah, let's say it's well posed, which is quite an assumption in the nonlinear case, but let's say you have a super nice Vlasov equation. So for every initial datum, you have a, let's say, unique weak solution. So essentially a unique solution path law Px. So you have this family. Does this family form a Markov process? And the answer is no. Please do not mix this up with the fact that each single Px or each corresponding stochastic process Xx does satisfy the what people often call the weak or elementary Markov property. But this family of path laws does not satisfy the Markov property. And the reason is basically that if you would want to prove the Markov property for this family, it essentially requires you to prove that, in a certain sense, this is linear in the initial datum, which is not true due to the nonlinearity imposed by the distribution dependence. But you can save the day by replacing the Markov property by a suitable so-called nonlinear Markov property. And if you look at this nonlinear Markov property, the left-hand side is exactly the left-hand side I showed you for the classical Markov property that we briefly discussed upon Jonas' question. But the right-hand side is something different. You see, in the right-hand side appears really the distribution of your original solution at the future or the present time s. Yeah. So what is this object here? So this is the solution to the McKean-Vlasov equation at this random initial condition. And I put this exclamation mark here to make you aware that you have to work to get this solution, because as I said, you cannot simply construct solution with arbitrary initial data by taking convex combinations of solutions with Dirac initial data, because you have a McKean-Vlasov equation. Or in other words, the corresponding martingale problem is nonlinear. Okay. So due to time constraints, let me not go into too much detail about this notion of nonlinear Markov property. Let me just shortly say it is really not.
Sorry, Marco.
Yeah, sure.
Sorry,
please.
Sorry if I interrupt. Can I ask
please.
a question?
Yeah, of course.
Thank you. Just to be sure that I understand correctly, because I've heard this paper presented already by a co-author of yours, and there's a point that I hadn't understood, and now that you're talking about this, I take the chance to maybe ask you. So, the way I understand it, if once you have your McKean-Vlasov, so if you fix the initial law and you look at the solution, so that is a diffusion. So that is a Markov process. What you're saying,
yeah, please.
If I understand, is that if I understand correctly, you're saying that where the Markov property fails is when you change equation. When you change, because for each Dirac delta you put as an initial datum, you're actually in a way changing the equation.
Why do you say you change the equation?
Way?
I mean, it's still the same equation. You just change the initial datum. I wouldn't call this changing the equation. You see, if you have an SDE, yeah, please.
Say you fix an initial distribution, like, and then if you go to the previous slide, for instance, I'm trying to make myself, okay, the equation, the McKean-Vlasov SDE.
Yes.
So say you fix the law of x0, and then if you look at it a posteriori, you have x solves in particular a standard SDE once you fix the law. So that is a Markov process.
In a sense, yes. So you're appealing to a very important point here, which is really at the core of what we do, even though it's a trivial thing. Namely, you're saying that if you have a solution to a McKean-Vlasov equation and you freeze, so you have a certain x which solves the equation, and you freeze this guy here, then all of a sudden you don't have a McKean-Vlasov equation, but you have a time-dependent standard SDE. And of course, your original solution will also solve this linearized equation.
Exactly.
Yeah, this is certainly true, but still, this is why I pointed this out. Please be aware, a Markov process is not one stochastic process. It's a family of path laws. Because again, if you just, so you see, you cannot formulate this property if you just have one path law, right? Because here, if this runs, you produce every possible WY. So what you're saying, and this is very much true, you're saying the following: if you have a solution to a McKean-Vlasov, like one single solution, and you do this freezing procedure, so you freeze a priori, you freeze the distribution of this given solution, you have a standard SDE. If you're lucky, and the standard SDE has a unique solution for every initial condition, which includes also all the initial conditions which are not related to the original one that you fix.
Exactly.
Then this gives you a classical Markov process. This is true, but this is a very different statement from saying that when you let your initial condition run here, so let's say it's Dirac, so x1, x2, x3, and you have a solution for every initial condition x1, x2, x3, you look at the corresponding solutions, they all solve the same equation, the same McKean-Vlasov equation. They do not solve the same frozen equation, but they solve the same McKean-Vlasov. Then this family does not satisfy the Markov property, which again is a very different statement from saying that each individual solution satisfies this elementary Markov property for which you don't need, so where you have a, you know, in a sense, much weaker and simpler formulation than this one.
Yeah, now you made it very clear. Thank you. That's what I meant by changing the equation.
Yes,
it was a bit
yes,
sloppy,
I see.
but that's exactly what I.
Yeah.
Okay, now I understand. Thank you.
Okay, sure. Okay, so just as a takeaway message here, to catch up on time, this nonlinear Markov property is really a strict generalization of the classical Markov property. So in a sense, if you have a classical Markov process, it always satisfies this nonlinear Markov property. The converse is not true. And this nonlinear Markov property is tailored in order to be satisfied by families solving a common McKean-Vlasov equation. So you can check right away, is a, say, 10-line proof that if you have a well-posed McKean-Vlasov equation, like you honestly have a unique solution for every initial condition x, and you look at the family of unique solutions, it satisfies this equation. This is a fairly short and simple proof, but it goes much beyond this. And okay, so what we need, so the cornerstone of our result is actually a previous result by Michael and myself from a previous paper where we also studied these nonlinear Markov processes in detail. And this is the result. So it appears quite technical, but let me walk you through this. Okay. Maybe let's forget about the subset of initial data. For us, let's just assume you have equality here. So you have all initial data. Okay, so let's say you have a solution to your nonlinear Fokker-Planck equation as shown above. You have a solution for every initial data, zeta being a probability measure, okay? So you have a solution for each initial datum, and you assume they satisfy sort of the, we call this flow property, is basically really just a semi-group property. And then the second condition is quite interesting. So what is this? And this comes back exactly to what you mentioned already about these linearized equations, but on the level of the PDE. So you do the following. You have your nonlinear Fokker-Planck, and for every given initial datum, zeta, you look at this specific solution. I am not claiming that these solutions are unique, okay? But I'm claiming that if you take this solution and you freeze it in the nonlinear Fokker-Planck, then you get this linear equation, right? Where this mu t that you solve for and the frozen guy here are not related, right? Trivially, this guy solves this equation because it solves the nonlinear equation, okay? So it also solves, in a sense, its own linearized equation. This is trivial but important because now you see, what is the condition? We have to verify that this guy, so it solves, of course, this linear equation, and since this is a linear equation, its set of solutions is convex, right? So you can look at its extreme points. And this specific solution, which need not be the only solution to this equation, but it's one solution, has to be an extreme point in the set of all solutions to this linear Fokker-Planck. And this you have to check for every mu zeta from your given solution, okay? This is quite, okay, sorry, and please forget, let's cross out this sentence. I don't have the time to explain this, it's not so important. I mean, technically it's very important, but for the presentation here, it's not so important. Okay, so.
So, sorry, Marco, so this is a specific example where the linearized Fokker-Planck doesn't have uniqueness, is that correct?
I wouldn't say it's an example where it doesn't have uniqueness, because from this situation you cannot prove that you have non-uniqueness, but it's not required that you have uniqueness.
Okay, so you admit the possibility that there is no uniqueness.
Definitely, okay. Yes, definitely. Okay, so if you're given such a situation, so one solution to the nonlinear Fokker-Planck for every initial condition, then the following is true. First of all, for every initial condition, again, forget about the P0 here, there is a solution to the McKean-Vlasov equation, which has these prescribed one-dimensional time marginals. This is not just some solution, but it's actually the unique solution to the McKean-Vlasov with these marginals, okay? And the family of the corresponding path laws forms a nonlinear Markov process. So in abstract terms, this theorem allows you, if you give me your favorite Fokker-Planck equation and you give me a family of solutions, they need not be unique, but you have one solution for each initial condition. And you tell me that these two conditions are satisfied, then I construct, or this theorem constructs for you a nonlinear Markov process whose one-dimensional time marginals are given by your originally given nonlinear Fokker-Planck solution family. And these are not just some, I mean, this nonlinear Markov process is not just some abstract object, but it consists of solutions to the corresponding McKean-Vlasov equation. And this is basically what I repeat here in words, but I mean, okay, if you like, I mean, have a brief look. Let's have like a 20-second break so you can read this and I can have a sip of water and then we go on.
I'm sorry, Marco, I have a question for you.
Please.
Is unicity required for the nonlinear Fokker-Planck equation at the very beginning?
Pardon, what is required?
So you start from a family mu of
Yes.
zeta of
Yes.
solutions to the nonlinear Fokker-Planck equation.
Yes.
Is
Yes.
unicity required here?
Sorry, what do you mean by the word unicity? Do you mean uniqueness or?
Yes. Uniqueness to the nonlinear Fokker-Planck equation.
No. This is not required.
So you don't need unicity.
No.
Uniqueness is not required.
No, it is just important. You have to have a family of solutions. I don't care whether for some or all initial data, there are many other solutions. You need that they behave well together because they need to have the semigroup property, which is immediately fulfilled if you have uniqueness. So uniqueness is a sufficient condition for I, but it's not required. Okay.
Thank you.
Sure. Okay, so this is what this general theorem does for you. I understand at the moment it might feel like we are quite far away from our specific p-Laplace case, but this will come. Precisely, it will come in 1 or 2 slides. There is one more slide before, because I need to make now the connection between these abstract nonlinear Fokker-Planck equations for measures, and proper PDEs. Okay, and the way to do this is the following. So nobody can stop you from considering a certain subclass of nonlinear Fokker-Planck coefficients where the dependence of your measure is not in a sense global via the entire measure, but it's pointwise via the density of the measure. Of course, in this case, you have to restrict your study to those measures for which a density exists, right? I mean, but you see, so this is usually called the Nemetsky case. So you have dependence on mu and x via considering the density u and evaluate it at x, and the same for b. Okay, and if you have such nonlinear Fokker-Planck equations, you can rewrite them as equations for the density u, and this gives you back a classical function valued PDE. Okay, so if you're saying, okay, I don't care about measure valued Fokker-Planck equations, this is abstract nonsense. I mean, it's not, but I mean, it's your right to feel about this this way, but then at least one has to acknowledge that there is a very interesting subclass contained, namely such nonlinear Fokker PDEs that you can treat in the spirit of Fokker-Planck equations. And then the corresponding McKean-Vlasov SDE, you can just write it down, right? Because you have the coefficients. We know what the McKean-Vlasov equation is. And you get this very, local, often degenerate, if you like, dependence on the density of the solution. Okay? And The analysis of such equations with these coefficients is really hard because you see right away that such coefficients are never regular, say not even continuous in their measure variable, okay? But this is not required in our previous result. So if you read this theorem, you do not find any kind of assumption on the regularity of the coefficients. Of course, you have to be able to solve the Fokker-Planck equation. So you might say, well, there is an implicit level of regularity that I need because else I can never expect to construct solutions. This is true, but the moral is really this. Suppose you have solutions. From that moment on, you need not any regularity on the coefficients, okay? So this is the moral. Okay, and okay, to keep this short, we implemented this theorem I showed you specifically for a certain class or for certain examples of such PDEs. For instance, for the Proust-Media equation, for 2D vorticity Euler and Navier-Stokes equations. So for solutions to such nonlinear PDEs, we constructed the corresponding McKean-Vlasov equation. We solved it to obtain probabilistic counterparts of these PDE solutions, and we proved the nonlinear Markov property. And exactly the same spirit we now want to employ for the p-Laplace equation. And this we do now. Okay, so we return to the p-Laplace equation finally. So this detour comes to an end now. And at first sight, you might be a bit suspicious whether you have any chance to writing this equation as such an equation. But you can do this. So we do two things. So we do two steps. First of all, basically just by a stupid integration by parts, if you like, we formally, I mean really formally first of all, not caring about any existence of differential operators whatsoever, we rewrite this right-hand side like this, okay? So we formally rewrite the p-Laplace equation as this nonlinear Fokker-Planck equation of this aforementioned Nemitsky type. Yeah, you see you have pointwise dependence on u here, and more precisely even on the gradient of u, and here even on the gradient of a certain power of the gradient of u. Okay, so these coefficients are quite involved. This is formal. Then we do something rigorous. And what we do rigorously is this. We show that whenever you have a solution to the p-Laplace equation, which satisfies a certain minimal regularity and integrability condition, then this u also solves this equation rigorously. So in the second step, there is nothing formal, okay? This is rigorous mathematics. Right, sorry, I didn't finish the sentence. So this is the minimal thing you need. And then this u also solves this equation if, in a sense, you have the minimal requirement that you can make sense of all appearing gradient terms. And by gradient terms, I do not mean these outer differential operators because you are in the distributional formulation. So these you put onto test functions, but you have to make sense of this gradient and this gradient of this power of the gradient. Okay. Okay, and I said already that this is really a nonlinear Fokker-Planck equation with these coefficients. Okay, so the coefficients do not only depend pointwise on the density, as I showed above in a general case, but on first and second order derivatives of the density. And this is really kind of a new class of coefficients, at least in this nonlinear Fokker-Planck business that we treat here with the first example. Okay, and then again, once you have this equation, you can at first formally write down the corresponding McKean-Vlasov equation. You just copy the coefficients in the right sense, right? So this you copy, and here you take again basically square root, and there might be a factor square root 2 missing here. But anyway, so this is your target McKean-Vlasov equation that we would like to show. And our first result is this. So start from a solution to the p-Laplace equation, yeah, with this regularity and a certain integrability condition that I do not want to go into detail. This is quite mild and usually satisfied, but you have to check it. Then there exists a solution to this McKean-Vlasov equation, which has these prescribed one-dimensional time marginal densities. Okay, so you give me a solution to the p-Laplace. I have to check this and this, then I can construct a McKean-Vlasov solution to this equation, which has the prescribed one-dimensional time marginals. So this is the first result, not yet related to the Barrenblatt solution, but we show that this result in particular applies to the Barrenblatt solution as follows. So now we come close to the main result, okay? So we show this previous proposition does apply to the Barrenblatt solution, okay? For every x, I said this before, this is a solution to the p-Laplace. We verify these integrability and regularity assumptions. So we apply the proposition. This gives us a stochastic process, so fix the initial condition. You get a stochastic process solving this above making Vlasov equation, and its one-dimensional time marginal densities are exactly the Barrenblatt solution started or with center of mass x. Okay, this is our first result, but we actually do much more. So we don't stop here. So this now finally, after sticking with me for 40 minutes, this is the main result, okay? So funnily, we do this only in dimension d greater equal 2. This is of course not because we think the case d equal 1 is more difficult, no, but you know, I mean, some Sobolev embeddings work differently, behave differently, dimension 1. And at the end of this paper, we were too lazy to explicitly write down additional arguments for the one-dimensional case. Okay, we do this for any p strictly greater 2. This is the following result. For every initial condition x, this making Vlasov equation from above has a unique weak solution. So meaning these guys that we constructed are the unique weak solutions with this constraint. So with the Barrenblatt one-dimensional time marginal densities. And they form, or more precisely, their path laws form a nonlinear Markov process. Okay? So you start from the Barrenblatt solution to the p-Laplace. You construct stochastic processes whose one-dimensional time marginal densities are exactly given by the Barrenblatt solutions. And these are not some abstract processes that you cannot get your hands on, but they solve an explicitly given making Vlasov equation, and they form a nonlinear Markov process. Okay, and then we were daring enough to give this a name and to really call this p-Brownian motion, or more precise. So the Markov process we call p-Brownian motion, and the specific member of this Markov process starting in x, we call p-Brownian motion started at x. And if you were to follow the construction that we do in the case p equal to 2, you would really get back classical Brownian motion in the end, sorry. Okay, so here's the comparison in words. So again, I recall for p equal to 2, you start from the heat equation, you have your fundamental solution, the heat kernel, and it determines you a unique classical Markov process, which in turn consists of the unique solutions to the associated SDE. Okay? And this Markov process is Brownian motion. We do, in a sense, exactly the analog. We start from the Barrenblatt solutions to the p-Laplace equation, and we show they determine a unique nonlinear Markov process consisting of the unique solutions to the corresponding Mackey-Vlasov equation. Okay, so the analogy is really close. Okay, so I have, okay, thanks to a former colleague of mine, Ehsan Abedi, who by now has graduated, so he's postdoc now. He, without even me asking for him, he followed our presentation on this paper by Michael, and he sat down and simulated these p-Brownian motion paths in dimension 1. And I think this is pretty cool. So you see, this is the growing support of the Barrenblatt solutions, okay? So at a time slice t, say t equal 4, this is the support of the Barrenblatt solution. So naturally, you don't see any path leaving this cone because this would correspond to a zero set of path. And I think this is quite neat. Okay, so maybe just 2 lines on the idea of proof. I'm not attempting to give any details here. So we want to apply our general construction result that I showed you. The flow property, so the semi-group property you can easily show. And then you have the strange extremality condition, if you remember this. And Okay, this is a technical thing that I don't have time to explain. So we can show that this extremality condition, you do not have to prove it directly for those solutions that start in a Dirac initial condition, but it suffices by some technical arguments which caused us quite a bit of pain. It is sufficient to prove this extremality condition for the Barenblatt solution started at a strictly positive time. Okay, so this delta is strictly positive, you see, and then you have to prove that the Barenblatt solution started at a positive time is an extreme point in the set of its own linearized equation where the initial datum is the strictly positive time. So this we showed, okay, I cannot explain here how we showed this, but can do this. And now this is the final thing I want to show, and this I think is really quite cool. Still, you might be nervous how in the world you prove this extremality condition. Yeah, I mean, how do you get your hands on this set of solutions to the linearized equation, and how do you prove extremality? This seems hopeless, and I agree. But luckily, we have this, from my perspective, pretty nice or cool lemma. And this tells you the following. So what you need to prove, so here I restate exactly what we have to prove, right? Namely that for every such Barenblatt solution from a strictly, so this you can forget, this is a typo. So for any strictly positive delta, you look at this Barenblatt solution starting from a strictly positive time. You want to show this extremality. And this holds if and only if you look to the set of all solutions to this equation in this class. What is this class? These are all solutions consisting of probability densities, weakly continuous in time, which are dominated by this specific solution. So this guy is certainly a solution to this equation. There could be many others. And you look not at the class of all solutions, but you only look at those solutions which are pointwisely dominated by the specific solution. This class is certainly not empty because the solution itself is contained in here. And this extremality condition notably can be characterized by uniqueness of solutions in this restricted class. So you transfer this extremality or geometric condition, you transfer to a uniqueness problem for this linear PDE. So you have to prove a uniqueness statement for this linear PDE, which you should not think is too easy because yes, it's linear, so this is nice, but it's highly degenerate because you see the diffusion coefficient has compact support in space. So it's 0 on a large portion of the space, so you're far away from an elliptic situation. But still, again, I don't want to give details here. We use the specific definition and properties of the Barenblatt solution, and then we could prove this. And just the final word, at least with our methods, proving this restricted uniqueness is hopeless for delta equal to 0, because then you have a Dirac measure here, and this guy for t going to 0 approaches the singularity and things break down, okay? It is sufficient to consider delta strictly positive, this we show, and for delta strictly positive, we can handle this. Okay, that's everything I wanted to tell you, so thanks a lot for your attention.
Okay, thank you very much. Thank you very much for a nice talk. And are there any questions or comments?
I have one question regarding the simulation of for p equal to 1.
Yes.
How did you obtain this by considering the Euler-Maruyama scheme of the Vlasov SDE?
Yes, exactly. So frankly speaking, since Esan did this, and I cannot give you any details on how he did this. It's quite a while ago that he sent this to me. So frankly speaking, I don't remember.
Okay.
Sorry.
No problem.
I have a short question, if
Please.
I may. So thank you, first of all, for the talk. So in many steps, it seems like you use very specific properties of the Barenblatt solution. So, however, the procedure you outlined seems like a very general procedure that could work anytime these properties, you have the right properties for the solution to the nonlinear PDE.
Yes, definitely.
So my curiosity is, have you already spotted other interesting nonlinear
Yes, we have. So yes,
do
we
the
have.
trick?
So first of all, we have this list, right? So we have the Prost-Media equation, we have 2D vorticity Euler and Navier-Stokes. A bit more recently, we treated the so-called Leibniz equation. The Leibniz equation is a generalization of the p-Laplace equation, where the right-hand side is not given by the p-Laplace operator. So this would be the p-Laplace equation, but you raise the u to a power, okay? So this generalizes at the same time the Prost-Media and p-Laplace equation, because for q equal 1, you have p-Laplace. For p equal 2, you have Prost-Media. So this is a doubly nonlinear PDE. And we were also successful for this case. And very recently, but this is still work in progress, with Shinichi Ota and Kohei Suzuki, we consider Finsler heat equations, so in a Finsler geometry setting, and also there we can construct the probabilistic counterpart by these methods.
I see. Okay, thank you.
Sure.
More questions? This Leibniz equation has a Barenblatt solution, right?
It does, yes.
Yeah, okay. I have a question about going beyond Barenblatt. So it seems that these properties are very difficult to prove for general p-Laplace equation on a domain. What if you use kind of heavy tools from analysis like regularity theory for nonlinear PDE? Is there any hope to check your conditions for?
Yes, I guess so. I mean, it's hard to say because we are relying so much on the specific Barenblatt properties, like really pointwise estimates and so on. But since we were successful also in other situations, and for example, so in this case, I mean, we didn't have any Barenblatt solutions at hand, so we worked in a certain general class of equations that was good enough to be treated by our methods. And I'm rather hopeful, I mean, seeing how robust this framework turned out so far, I'm rather hopeful that one can go in this direction, yes.
Okay, thank you.